Determining the correct wire size for a 480 volts three-phase service running a distance of 2000 feet involves several factors. A formula can be used to approximate the wire size needed. The formula is wire size equals total load current multiplied by distance multiplied by correction factor, all divided by voltage drop. Several assumptions are made to use this formula because of missing information such as total load current. A total load current is unknown. For calculation purposes, let's assume 100 amps. The distance is 2000 feet, which is the one-way distance from the service to the load. The correction factor is 1.25. This is an adjustment for three-phase calculations. The voltage drop is 3%. This is an acceptable voltage drop for most applications. To determine the appropriate wire size, one can use the National Electrical Code, or NEC, wire tables and online wire calculators. According to the NEC wire tables, a load current of 100 amps at 480 volts requires a minimum of a 250 kc mil wire. Using online wire calculators, you may find variations in the recommended wire size. Firstly, calculator 1 may suggest 2/0 American wire gauge, or AUG. Secondly, calculator 2 may suggest 1/0 AWG. Thirdly, calculator 3 may suggest 3/0 AWG. Based on the NEC wire tables and the various calculator results, a recommended minimum wire size for running a 480 volts three-phase service 2000 feet is 1/0 AWG. However, the actual wire size required may vary depending on the specific load and voltage drop requirements. It is always advisable to consult with a qualified electrician to determine the appropriate wire size for a specific application. The NEC provides tables that specify the allowable ampacities of conductors based on their size, insulation type, and installation conditions. These tables, such as NEC Table 310.15, B16, are crucial for determining the minimum conductor size required to carry a given load current without overheating. Voltage drop is a critical factor in long-distance power transmission. Excessive voltage drop can lead to reduced equipment performance, inefficiency, and potential damage to connected devices. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits. To calculate voltage drop, the following formula is used. Voltage drop equals 2 multiplied by the current multiplied by the length multiplied by the impedance, all divided by 1000. The impedance values can be obtained from NEC Chapter 9, Table 9. Keep in mind that the ambient temperature affects the ampacity of conductors. Higher temperatures reduce the conductor's ability to dissipate heat, thus lowering its ampacity. NEC Table 310.15, B2. Provides correction factors for ambient temperatures other than 30 degrees Celsius or 86 degrees Fahrenheit. When conductors are bundled together or installed in conduit, their ability to dissipate heat is reduced. NEC Table 310.15, B3. Provides adjustment factors for the number of current-carrying conductors in a raceway or cable. These factors must be applied to the conductor's ampacity to ensure it does not exceed its rated limit. The type of insulation used on a conductor affects its temperature rating and ampacity. Common insulation types include THHN, THHW, and XHHW. Each type has different temperature ratings and suitability for various environmental conditions. The selection of the appropriate insulation type is crucial for ensuring the long-term reliability and safety of the electrical system. Grounding conductors play a vital role in electrical safety by providing a low impedance path for fault currents to return to the source. The size of the grounding conductor must be adequate to safely carry the maximum fault current that could occur in the system. NEC Table 250.122 provides guidelines for sizing equipment granting conductors based on the size of the overcurrent protective device. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. The size of the overcurrent protection device must be matched to the ampacity of the conductor it protects. NEC Section 240.4 provides rules for the protection of conductors against overcurrent. Conduit is used to protect conductors from physical damage and environmental factors. The type and size of conduit must be appropriate for the number and size of conductors it contains. NEC Chapter 9 provides guidelines for conduit fill, ensuring that the conductors can be easily installed and that heat can be adequately dissipated. For long runs, consider using aluminum conductors instead of copper conductors. Aluminum is lighter and less expensive than copper, but it has a higher resistance. This means that a larger size aluminum conductor will be required to carry the same amount of current as a copper conductor. However, the weight savings can be significant, especially for long runs. When using aluminum conductors, be sure to use connectors and terminals that are specifically designed for use with aluminum. Aluminum oxidizes quickly when exposed to air, and this oxidation can create a high resistance connection if not properly addressed. Using the correct connectors and terminals will ensure a reliable and safe connection. The NEC requires that all electrical work be performed in a neat and workmanlike manner. This means that conductors must be properly supported, labeled, and terminated. It also means that the installation must be aesthetically pleasing and easy to maintain. A well-installed electrical system is not only safer but also more reliable and easier to troubleshoot. Before starting any electrical work, it is essential to obtain the necessary permits from the local authorities. Permits ensure that the work is inspected and meets all applicable codes and regulations. Working without a permit can result in fines, delays, and even legal action. Always check with the local authorities to determine the permit requirements for your project. After completing the electrical work, it is important to thoroughly test the system to ensure that it is working properly and safely. This includes testing for voltage, current, continuity, and insulation resistance. Any problems that are identified during testing must be corrected before the system is put into service. Proper testing is essential for ensuring the safety and reliability of the electrical system. When sizing conductors for long runs, it is important to consider the effects of harmonic currents. Harmonic currents are non-sinusoidal currents that can cause overheating of conductors and equipment. If harmonic currents are present in the system, the conductor size must be increased to compensate for the additional heating. A qualified electrical engineer can perform a harmonic analysis to determine the appropriate conductor size. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, switching transients, and other events. SPD should be installed at the service entrance and at any sensitive equipment locations. The size and type of SPD must be appropriate for the voltage and current levels in the system. Proper surge protection can significantly reduce the risk of damage to electrical equipment. When installing conductors in underground locations, it is important to protect them from moisture and physical damage. This can be achieved by using direct burial-rated cables or by installing the conductors and conduit. Depth of burial must also be in accordance with the NEC requirements. Proper underground installation will ensure the long-term reliability of the electrical system. In corrosive environments, such as those near saltwater or chemical plants, it is important to use conductors and equipment that are specifically designed for these conditions. This includes using corrosion-resistant materials such as stainless steel, PVC-coated conduit, and epoxy-encapsulated transformers. Proper material selection will prevent premature failure of the electrical system due to corrosion. When working on electrical systems, it is essential to follow all safety precautions. This includes wearing appropriate personal protective equipment such as gloves, safety glasses, and arc flash-rated clothing. It also includes de-energizing the circuit before working on it and verifying that it is de-energized using a voltage tester. Following safety precautions will prevent electrical shock, arc flash, and other injuries. Regular maintenance is essential for ensuring the long-term reliability and safety of electrical systems. This includes inspecting conductors, connections, and equipment for signs of wear, corrosion, or damage. It also includes testing overcurrent protection devices and ground fault circuit interrupters, or GFCIs. Performing regular maintenance will identify potential problems before they lead to failures. When sizing conductors for motors, it is important to consider the motor's starting current. The starting current of a motor can be several times higher than its running current. The conductor size must be adequate to handle the starting current without excessive voltage drop. NEC Section 430 provides detailed rules for sizing conductors for motors. Power factor correction capacitors can be used to improve the power factor of an electrical system. A low power factor can result in increased current flow, higher energy losses, and reduced equipment capacity. Installing power factor correction capacitors can reduce these problems and improve the overall efficiency of the electrical system. The size and location of the capacitors must be carefully selected to achieve the desired results. Energy-efficient transformers can significantly reduce energy losses in electrical systems. These transformers are designed to minimize core losses and copper losses, resulting in lower operating costs. Energy-efficient transformers are particularly beneficial in applications where the transformer is continuously loaded. The use of energy-efficient transformers can also reduce the environmental impact of the electrical system. When sizing conductors for nonlinear loads, such as electronic ballasts and variable frequency drives, or VFDs, it is important to consider the effects of harmonic currents. Nonlinear loads generate harmonic currents that can cause overheating of conductors and equipment. The conductor size must be increased to compensate for the additional heating. A qualified electrical engineer can perform a harmonic analysis to determine the appropriate conductor size. Uninterruptible power supplies, or UPSs, are used to provide backup power to critical equipment during power outages. The size of the UPS must be adequate to handle the load current of the equipment it supports. The UPS must also be properly maintained to ensure that it is ready to provide backup power when needed. Proper UPS sizing and maintenance are essential for ensuring the continuous operation of critical equipment. When installing conductors in hazardous locations such as those containing flammable gases or dust, it is important to use conductors and equipment that are specifically rated for these locations. This includes using explosion-proof conduit fittings and enclosures. The installation must also comply with the NEC requirements for hazardous locations. Proper installation in hazardous locations will prevent explosions and fires. When working on electrical systems, it is important to be aware of the potential for arc flash. Arc flash is a dangerous electrical explosion that can cause serious burns, injuries, and even death. Arc flash hazards can be reduced by using arc flash rated equipment, wearing appropriate personal protective equipment, and following safe work practices. An arc flash risk assessment should be performed before working on any electrical equipment. When sizing conductors for renewable energy systems such as solar photovoltaic or PV systems and wind turbine systems, it is important to consider the specific requirements of these systems. This includes considering the voltage, current, and operating conditions of the system. The conductor size must be adequate to handle the maximum current that the system can produce. The installation must also comply with the NEC requirements for renewable energy systems. Proper sizing and installation of conductors in renewable energy systems will ensure the safe and reliable operation of the system. In high-altitude locations, the air is thinner, which reduces the cooling effect of the air on conductors and equipment. This means that the ampacity of conductors must be dilated to compensate for the reduced cooling. NEC Table 310.15 V2. V provides correction factors for altitude. When sizing conductors for direct current or DC systems, it is important to consider the voltage drop. DC voltage drop can be more significant than alternating current or AC voltage drop, especially for long runs. The conductor size must be increased to compensate for the voltage drop. The voltage drop can be calculated using Ohm's law. Proper sizing of conductors in DC systems will ensure that the equipment receives the correct voltage. When installing conductors in wet locations, it is important to use conductors and equipment that are specifically rated for wet locations. This includes using waterproof conduit, fittings, and enclosures. The conductors must also be insulated with a moisture-resistant material. Proper installation in wet locations will prevent corrosion and electrical shock. When sizing conductors for electric vehicle charging stations, it is important to consider the charging current and the duty cycle. The charging current can be quite high, especially for fast charging stations. The duty cycle is the percentage of time that the charging station is in use. The conductor size must be adequate to handle the charging current and the duty cycle. The installation must also comply with the NEC requirements for electric vehicle charging stations. Proper sizing of conductors for electric vehicle charging stations will ensure safe and reliable charging. When installing conductors and cable trays, it is important to follow the NEC requirements for cable tray installations. This includes properly supporting the cable tray, using the correct type of cable, and maintaining adequate spacing between cables. The cable tray must also be properly grounded. Proper installation of conductors and cable trays will prevent damage to the cables and ensure the safe operation of the electrical system. When working on electrical systems, it is important to use the correct tools and equipment. This includes using insulated tools, voltage testers, and ground fault circuit interrupters, or GFCIs. The tools and equipment must be in good working condition and properly maintained. Using the correct tools and equipment will prevent electrical shock and other injuries. When sizing conductors for data centers, it is important to consider the high density of equipment and the need for reliable power. The conductor size must be adequate to handle the load current and the voltage drop. The installation must also include redundant power systems and backup generators. Proper sizing and installation of conductors in data centers will ensure the continuous operation of the equipment. When installing conductors in healthcare facilities, it is important to follow the NEC requirements for healthcare facilities. This includes using isolated power systems, ground fault protection, and redundant power systems. The installation must also be designed to minimize the risk of electrical shock to patients and staff. Proper sizing and installation of conductors in healthcare facilities will ensure the safety of patients and staff. When working on electrical systems, it is important to be aware of the potential for electromagnetic interference, or EMI. EMI can cause malfunctions in electronic equipment and can disrupt communications. EMI can be reduced by using shielded cables, grounding the equipment properly, and installing filters. When sizing conductors, it is important to consider the effects of skin effect. Skin effect is the tendency of alternating current to flow near the surface of a conductor. This effect becomes more pronounced at higher frequencies. Skin effect can increase the resistance of the conductor and reduce its ampacity. The effects of skin effect can be reduced by using larger conductors or by using conductors with a larger surface area. When installing conductors in parallel, it is important to follow the NEC requirements for parallel conductors. This includes using conductors of the same size, material, and insulation type. The conductors must also be terminated in the same manner. Paralleling conductors can increase the ampacity of the circuit and reduce the voltage drop. However, it is important to ensure that the conductors are properly installed and balanced to prevent overheating.